Hi, I'm Tom Lee. Welcome back. Today we will talk about the mass spring system without damping or with damping. This is a second order differential equation. So you can see a spring in here. These springs will bouncing up and down. Let's see some animation GIFs about the springs before we go into the second order differential equation and how to solve it. Okay, you can see a spring is bouncing up and down. And this is another example of a springing system. When you roll the ball here, the ball will go down into the tunnel. And then this one is a springing system with a very heavy damping. So it's no vibration in here. Just stop at this equilibrium state. And this springing system is without any damping at all. Though the springs will vibrate infinitely with a cycle. And this one is displacement type graph and the velocity type graph of the springing system. You can see this springing system with very little damping of 0.4 Newton second meter. Okay, this spring system on the left hand side, the spring system with a bit of damping, and on the right hand side, the damping is very heavy, so the spring stop more rapidly. So until now, you must understand what is a springing system. Then we go into the mathematical part to calculate the second order differential equation of a springing system, and we solve it. Now let's get into a spring system question. We have a force of 18 Newton stretch a spring of 0.8 meter. A mass of 10 kg is attached to the end of the spring. This is the mass. Let's see if this is 10 kg. And then release 1 meter below the equilibrium position. So what is the equilibrium position? Without any external force, when you hang a mass here, the mass will stop in here. This position is called the equilibrium position. And then we pull down the mass for 1 meter. So 1 meter below the equilibrium position with an upward velocity. If we release the mass, then the springs will spring up. Initial velocity will be 0.5 meters per second. And adopt the G. What is the G? The G is the gravity of the Earth. Let's say the gravity of the Earth is 10 meters per second square. And now we want to calculate the equation, the displacement equation. Let's say it's y, t is equal to some function of t. What we want to do is to get this function. And now we go to the mathematical part. Now get our hand dirty and we go to our mathematical parts and calculate the differential equation in second order and solve it. First thing first, we will find the equation of the motion. We need to analyze the spring's mass system using the principles of physics. And we will determine the spring constant K, the equilibrium position, and the subsequent motion of mass. Let's determine the spring's constant K. Given that the force is equal to 18 Newton, and the displacement is x equal to 0.8 meter. Because we sketch a spring of 0.8 meter with 18 Newton of force. And then by the Hooke's law, we have the force is equal to the K, the spring's constant, multiplied by x, the displacement. So K is equal to F over x, equal to 18 Newton over 0.8 meter. So it's equal to 22.5 Newton per meter. We have calculated the values of K. Then we determine the equilibrium position of the system. The equilibrium position xe is where the spring's force balances out the weight of the mass. In this example, our mass m is equal to 10 kg, and the gravitational acceleration of the Earth is about 10 meters per second square. The weight of mg is mg equal to 10 kg multiplied by 10 meters per second square equal to 100 Newton. And at equilibrium, k times ex is equal to mg. And from the above, we know that k is equal to 22.5, so it's times the xe is equal to 100, so xe is equal to 100 over 22.5 and equal to 4.44. With the values of xe's and the values of k's, we then formulate the differential equation of the motion. Since this spring system is without damping, so the motion of the mass spring system can be described as below. m d2 squared by dt plus c dy by dt plus ky equal to 0. And because it's no damping in this system, so c is equal to 0 in here. So this one can be cancelled out. And we have m y dash dash plus ky equal to 0, where y is a function of t. And then we plug in the values of m and k. We have 10 y dash dash plus 22.5 y equal to 0. And we simplify it to y dash dash plus 22.5 over 10 y equal to 0. Finally, we get the differential equation y dash dash plus 2.25 y equal to 0. Since this is a simple harmonic oscillator equation with angular frequency omega given by omega squared equal to 2.25, so omega is equal to square root of 2.25 is equal to 1.5 radian per second. Then we solve the differential equation as below. The general solution is y of t is equal to c1 cosine omega t plus c2 sine omega t, where c1 and c2 is constant. From the initial condition, we have y0 equal minus 1, and y dash 0 is the velocity equal 0.5 meter per second. And if we differentiate yt, we got the y dash t is equal to minus c1 sine omega t multiplied by omega plus c2 cosine omega t. We substitute y0 equal minus 1 into the yt equation. We got c1 is equal to minus 1. And we substitute y dash 0 equal to 0.5. We have y dash 0 equal to 0.5 equal to omega c2. c2 is equal to 0.5 over omega is equal to 1 over 3. So we get two values of c1 and c2. We substitute into the original equation of yt. We have yt is equal to minus cosine 1.5t plus 1/1 of sine 1.5t. And finally, we have found the motion equation of this spring system. And after the break, we try to determine the period 1 cycle of the spring system. So the period, the time taken to complete one cycle of the oscillation, is actually the reciprocal of the frequency f, where the equation omega equal to 2 pi f. So f is equal to the omega over 2 pi. And the period t is equal to 2 pi over omega, where omega is 1.5 radian per second. Therefore, the period of this cycle is 4.9 seconds. And question again, as 11 seconds after the mass is released, try to find the location relative to the equilibrium position. We just substitute t equal to 11 into yt, and we have y11 equal to minus cosine 1.5 times 11 plus 1/1 of sine 1.5 times 11. Then it's equal to minus cosine 16.5 plus 1/1 of sine 16.5. And cosine 16.5 is approximately equal to minus 0.7024. And sine 16.5 is approximately equal to minus 0.7118. Therefore, y11 is approximately 0.7024 plus minus 0.7118 over 3. The answer is 0.4665 meter. Since this one is a positive answer, so the mass is now above the equilibrium position by 0.4665 meter. We have done. We now extend the question. Suppose that the spring system in A is released again, but this time in a medium that exerts a viscous resistance of 90 Newton when the mass has a velocity of 3 meters per second square. So it's actually a damping system. In a damping system, the general equation would be my dash dash plus cy dash plus kx equal to 0, where c is called the damping coefficient, and k is the spring's constant. M is of course the mass. And now let's see how we calculate the c, the damping coefficient. The equation of c, the damping coefficient, is the damping force over the velocity. So it's equal to 90 Newton over 3 meters per second, and this is equal to, of course, 30 kilograms per second. This is the damping coefficient of this medium. and we substitute into the differential equation, we have 10 d2y by dt squared plus 30 dy by dt plus 22.5y equal to 0. So what is the characteristics of this spring mass damping system? We can say that this is a second-order linear differential equation with both the spring force and the viscous damping force as well. And finally, the type of this damping system involves the motion is called the viscous damping. So very good for today's lesson. If you want to learn more about the differential equation in second orders or first orders, let's watch my next videos or the future videos. If you like these videos, please subscribe to my channels, and good luck and have a good day. Bye bye. Adios. Hasta la vista.